Hello, everybody. My name is Rachmat. I am from the Organic Chemistry class made by Padam, and here I'm going to discuss the four models that has been given for the trigger questions. So let's go start now, shall we? Okay. So the first thing is about polymer basics. The basics of polymer. What are the questions that have been provided? Where the first one would be define the term polymer and how is it different from a small molecule. So, a polymer is a large molecule composed of repeating structural units, monomers. Where these monomers are linked by covalent bonds. Unlike small molecules, the polymer have high molecular weights and unique physical properties. For the second question is what is a monomer? We mentioned monomers and what is a repeat unit? And give two examples, of course, of these common repeat units. So a monomer is a small molecule that can join with other to form a polymer, which we mentioned. And what is a repeated unit? And the commons what are ethylene, with ethylene becoming polyethylene, and vinyl chloride become polyvinyl chloride. So you see how there's going to be a difference when it transforms into the poly version. So the third is going to be what is the degree of polymerization, which is shortened as DP, and how is it calculated? So this is the number of the repeating units in a polymer chain. DP, as in the molecular weight of polymer, molecular weight of repeated unit as well. And it's also telling us to define and explain the number average molecular weight, which is Mn, and also weight average molecular weight, which is Mw, and polymer dispersity index, which is shortened as PDI. So the Mn, which is the number average Mw, it is the sigma Nm divided by sigma n. And for the Mw, is also the same except it's Nm squared divided by Nm, with PDI being M divided by M, which is the differences. It indicates the distribution of breadth. And then we can go and move on to the fifth question, which is the significance of molecular weight. So, high molecular weight polymer generally shows better mechanical strength, thermal stability, and viscosity. Meanwhile, low molecular weight polymers have lower strength and processability advantage. With the classifications, they would be given as three: the source natural, it is natural, the source, and and it's also there's also synthetic one, and also there's semi-synthetic. Let's say natural being rubber, and synthetic being polyester, and semi-synthetic would be cellulose. And there's a thermal behavior, which three, which is thermoplastic, which we all know, thermoset, and also elastomer, which is the normal classification for thermal behavior. For the architecture, there's a linear, a branch, and a crosslink, which can be illustrated in many different ways. So the real world examples being, let's take one of the classifications being thermal behavior. First, we have thermoplastics. We can use this plastic bottle right here as a thing for thermoplastic, and there's thermoset for electrical insulators, which I can't show here at the moment, and elastomer, which is rubber bands, which there isn't any here, but they all have an elastic deformation. They go back to their own current state. Now, for the second part of the model, which is the step growth polymerization. Okay, so we can move on to the first question being this step growth polymerization. What is it exactly? So it is technically a polymerization where two molecule species can react, typically involved by functional groups like um, oxygen hydroxide with COO and nitride hydrogen. And there's a second question which explain the difference between step growth and chain growth. Of course, we're going to talk about chain growth later on, but the step growth is a polymer where it grows via reactions between all monomers, oligomers, and polymers. And there's a slow molecular weight buildup. Meanwhile, the chain growth goes by addition to active site on a growing chain, and it has a rapid molecular weight buildup, early stages. And it also we have to describe the formation of PET from ethylene glycol and terephthalic acid. And also we have to explain the repeat unit of it. So PET, which is polyethylene terephthalate, is made from ethylene glycol and terephthalic acid, and the repeat unit on it is OCH2, CH2, OCO, C6H4CO. So we also have to describe the formation of nylon 6.6 from the hexamethylene diamine and adipic acid. And what is the linkage time? So what we made from the hexmethylene diamine plus the adipic acid, we have a linkage from the amide bond, which is CO and H, forming a polyamide. Then we move on to what is important to remove: water or other byproducts during stem growth formation. Well, as we can see, if we remove the water, it removes the shifts equilibrium forward and increasing polymer yield and molecular weight. When we also have to write and explain Carothers equation and how is it used to determine degree of polymerization. So the equation is dp equals 1 divided by 1 minus p, where p is a fractional monomer conversion, my bad, and shows how high conversion is needed for high dp in step growth. Why do we need that? Because if you look at it being higher in conversion, it has a better value, of course. And where we have to calculate dp in the monomer conversion is 98%. So if it's 98%, meaning that it would be 0.98, because it's 0.98, one negative 0.98, it turns into 0.02. So the one on the top, which is 1 divided by 0.02, it shows a more higher dp value. As I mentioned, the higher the p is, the better the value is. And the interpretation is each polymer chain has at least 50 repeated units and moderate polymerization. And also, um, fractional monomer conversion is in percentage. And also, we have to compare the mechanical application properties of PET and nylon 6.6. Like before, while PET is strong, transparent, and used in bottles and textiles, as we can see like this. Nylon 6.6 is tough, abrasion resistant, and it's used in fibers and ropes. So it is stand hard and more tough for heavy lifting and everything else. And we also have to explain the thermodynamics and reaction conditions, and also how it affects polymerization yield. Now, the negative Gibbs free energy is favorable, and also the high temperature and vacuum drive off small molecules, which increases the yield. Now we move on to the third module, which is chain growth polymerization. Now, the first question of chain growth polymerization, we have mentioned chain growth polymerization before. So the first one will be, what is chain growth polymerization? We have mentioned before when it was compared with the previous one. So chain growth polymerization is when a polymer is goes by successive addition, as we mentioned, of monomers to an active site. Which it could be radical, it could be cation, it could be anion, and it differs from stud growth in that only active centers grow the chain, and this chain polymerization starts to affect and occur, of course. And we have to describe the three main steps of free radical polymerization, which is initiation, propagation, and termination. First, we have initiation, where the radical is generated via, let's say, benzonyl peroxide or ABN. And also, there is propagation, where the monomer adds the red to the radical, extending the chain further. That's why there's chain growth. And the termination, where the two radicals combine or disproportionate to end growth. So it stops the growth after using this chain mechanism to start making itself much more bigger, much more, of course, extended. And then the third question is, explain how initiators like benzoyl peroxide, we have mentioned as the initiation, or ABN work also, and why are they needed? So the compounds like benzoyl peroxide generates radicals that start chain reaction needed to form active centers. Because of these radicals, it's becoming to the to the second step, my bad, which is the propagation in the previous question. Now, we have to compare free radical, cationic, and anionic in polymerizations in terms of three things, which is initiator, stability, and mechanism. For the initiator, we have radical for the radical, and acid or base for the cationic or anionic. So the stability, meanwhile, with radicals, they are moderately stable. But anions and cations, because they have a initiator of acid and base, they require a careful control when compared to radicals that are moderately stable. The mechanism is all involve initiation, propagation, and termination, just like we mentioned, which is the three main steps, but not always in living systems. And then we move on to the fifth question, which is, what is living polymerization? That is one of the questions. And how does it enable better control over molecule weight and structure? So no termination or chain transfers makes it so the chain keeps growing as long as the monomer is still present, which allows precise control or molecular weight and architecture. That is it. So if it doesn't get terminated, the chain keeps on extending as long as there is a monomer present. So now we have to describe PE, which is uh, made by free radical polymerization. And the answer is high pressure polymerization of ethylene with radicals leads to branch structure which have low density. So now we have to describe how PP is made using Ziegler-Natta catalyst. What makes this method unique as well? So coordination polymerization using TiCl 4 and Al, which is aluminum Et3 catalyst, allows stereoregular isotactic PP, unlike random toxicity in radical methods, which are more stable, as we mentioned. And now we have to discuss we have mentioned about PE, we have mentioned about PP. Now we have to at least explain the difference in properties of P and PP. So PE is more flexible and has a lower melting point than PP. Meanwhile, PP is more rigid, it has a higher melting point, and it's a better in strength. So PP is polyethylene, and the structure affects crystallinity and mechanical properties, of course. And so for the ninth and tenth question, it talks about the effects on PS on PVC. So the polymerization method, which either be controlled or radical, it affects the toxicity with the branching, adaptive properties like toughness and flexibility of the material. And the tenth question is the chain transfer. So this transfers active site to another molecule. It limits the chain length and molecular weight and can be deliberate to control molecular weight or unintended. As if we control this, we have to limit the chain length so it doesn't go as further as we cannot predict it to be. So the fourth would be in the model is talk about copolymer. So what is copolymer exactly? So copolymer is made from two or more different monomers. There's also a homopolymer has only one type of polymer. So there's co and homo. That is the difference between the two of them, and we have to describe and illustrate. So um, there's the random copolymers. They're like, so let's say there's monomer A and there's monomer B. They are there, but they are arranged randomly, so we do not know where the position of these two monomers are. Meanwhile, block copolymer, where there's going to be a long block of the A polymer, it is followed by another block of the B polymer. And also, the graph polymer is where there's going to be chains of the B polymer, which is grafted onto the backbone of A. This is A, and this is B right on it. And there's a multi-block copolymer, which is alternating multiple short blocks of A and B, meaning this is going to be A, B, A, B, A, B. Some say like a pyramid, of course. And then how is a random copolymer synthesized? What are its properties? So formed via free radical polymerization of a monomer mixture, properties being amorphous, of course, being the single, intermediate, and between homopolymers, as we mentioned. And the fourth is how is a block of polymer synthesized? And explain using living controlled polymerization. So when we use living polymerization to add one monomer, which is the A, and then the second one B, it forms an AB because they're both has to be connected, and this requires no termination. Just let them be synthesized. So, for the fifth question, my friend, it is what is the role of RAF or ATRP in making block copolymers? RAFT or RAF and ATRP allows controlled living radical polymerization, which enables precise block length and narrow molecular weight distribution. Just like chain growth, it stops the length of the chain growth and also makes it more durable and more controllable to have more precise and more narrow molecule weight, whatever your mind contends, but it's at least, let's say, customizable. So and then we have to describe the grafting form and grafting onto techniques when each is preferred. So the grafting form, it grows side chains from the main chain. So when the chain is going up, there's going to be chains going to the other ways around. And there's a grafting onto where preformed chains attach to main chain. So there was chains that had been formed before, but they have been limited by their length. They connect to the new chain that has been made and starting to extend. And the preference meaning as From it gives higher graph density, meanwhile onto allows pre-control of side chains because it is better to analyze, it is better to control when there are no side chains that are producing from the main chain. And then the seventh one would be what are the performance advantage of multi-block polymers? So the multi-block, as you mentioned, it has a bunch of like monomer A, monomer B, and a bunch of things. It combines the properties of both blocks as the two blocks starts to connect and starts, of course, making a pyramid or some such. Its strength of one plus elasticity of another, better phase separation, and mechanical behavior because they have mixed and be formed into one, and provide one real-world example for each type of architecture and relative relate structure to function. So the random is SBR, let's say tires, with the block, let's talk about shoe soles, which is styrene butadiene styrene. If you've seen your shoe sole, you know how hard it is, you know how bonded it is. And of course, let's say for the graph, let's say impact resistant plastic, which isn't common in the world, of course, but that's one of the example with multi-block thermoplastic and elastomers. You can, as with thermoplastic being the bottle and everything else, those are multi-blocks. So the ninth and tenth, which are the two last questions, which being phase separation and block polymers. So the blocks are immiscible and spontaneously separate into domains, which leads to nanostructures and unique mechanical and thermal behavior because of these two being mixed and they have separation into different domains. They have different behavior for each domain. And for the last question is design of block polymer, uh, the block copolymer, my bad, and the application of it. So let's say design it being hydrophilic and phobic, as it, of course, absorbs moisture. We can take PEG, PLA as one of the examples. So drug delivery where PEG ensures solubility, and the solubility goes from hydrophobic because it absorbs more moisture, and it the PLA it allows biodegradability. That's why it's hydrophilic, making it so it is more recyclable and other things around the way. That is it, Ashley, for the trigger question. Thank you very much for having watching this almost 18-minute video of me explaining. I hope I have done a very great job. Thank you, Pa Adam. Thank you, everyone else. And I will see you later. Hopefully, this has been helpful. Goodbye. And this has been Ridwan Rachmat. Stay tuned.